mechanics to fluid mechanics. We have already seen the definition of a fluid, and we have already talked a bit about the difference between solids and fluids. Does anyone remember? In terms of quantities which we have studied, what is the difference in the behavior of a solid and a fluid? Which deformation? What type of a force will a fluid resist? Or will a solid resist? Well, both resist actually, but there is a difference in the behavior, and the difference comes in the action of a shear force. When a shear force is applied on a fluid, it continues to deform, whereas when you apply a shear force on a solid, which we have seen, it deforms, but then the deformation comes to an equilibrium. In a fluid, the deformation continues, and this is, you see it when you stir a cup, when you stir a spoon in a cup. As long as you keep on stirring, basically you are applying a shear force in a tangential direction, and the fluid keeps on moving. It doesn't stop. Whereas it's the same thing with a solid, and you take a bar and you apply a torque on it, what happens? It resists, but it stops. So, the basic difference, and this is reiteration, between a solid and the fluid is the response to a shear force. I have just written what I said, that a solid, when applied with a shear force, comes to an equilibrium deformation, whereas a fluid, when applied with a shear force, continues to deform, I have used the word continues twice to emphasize that, continues to deform continuously, however small the shear force may be. Probably wrong English, but pardon me for that. That's correct. Okay. So now, that means if a normal force is applied on a fluid, will it deform or will it not deform? And the answer is, it may deform, but it may also not deform. And the example of that is, we have seen that if you have a glass in which water is kept, you go at some depth below, there is a pressure which is acting. And the pressure means a normal force. So while the normal force is acting, the fluid does not deform. That is one point. So to qualify this, point number A is under the action of a normal force, fluid may or may not deform. And the second thing is that while the fluid element deforms continuously under the action of a shear force, it does offer a resistance. It is not that you apply a force and there is no resistance. And one way to see this is that if we apply a torque, then you know torque is equal to I alpha. A very basic relation. Of course, the relation is much more general than this, but in general you can say torque is equal to I alpha. So if T is not equal to 0 and there is no resistance, this will imply alpha is not equal to 0. And this will imply that omega keeps on increasing. Okay, if alpha is not 0, just think of a simple case. If alpha is constant, omega will be alpha t. But what we observe is that if a continuous deformation shear force is applied, the fluid does come to an equilibrium omega. If you are stirring it with the same angle, this thing, it will come to a constant speed. So that means the resistance does not show up at the deformation level, but it shows up at the rate of deformation level. So what this implies is that the resistance of the fluid shows up at the or as rate of resistance. So now broadly, how will this show up in our governing equations? Let's try to see that. So broadly, I'm just right now not doing a full technical analysis. How will this show in the governing equations? In solids, at least for linear solids, what we got was that stress was proportional to strain. Because what is strain? Strain is deformation, a non-dimensionalized deformation. Okay? So now, what would we expect in fluids? What would stress be proportional to? Rate of strain. Instead of strain, what we will expect is in fluids, stress will be proportional to the rate of strain. And this is the big difference in the constitutive nature of solids and fluids. Is that clear? That in fluids, it will, so there is a resistance in the fluid, but the resistance shows up at the level of the rate of strain. And the property, we had this Young's modulus, which related stress to strain. In fluids, the property which will relate stress to the rate of strain, or that proportionality constant for linear fluids, will be termed as viscosity. So, the property of the fluid which resists the shear stress and relates it to the rate of strain is called viscosity, or technically the in our course we will be using the coefficient, we will use the term mu, but so far in schools and coaching maybe you have heard it as eta. So this is the eta which you have talked, which you must have seen, is the property called the viscosity, and that is what we are talking of when we talk of fluid mechanics. Okay, so this was the broad introduction as to what a fluid is and how it differs from solids. But then the concepts which we have done for stress, they still stay. Only some nomenclature will change, but things like Mohr circle and all, while we do not use that in so much in fluid mechanics, but will still be valid. That if you have to shift the angle, you want to find the stress in some other plane, then you, if it's a two-dimensional situation, you can still use Mohr circle. If it's a three-dimensional case, then you have to look at the principal axis, then draw three Mohr circle, and they will give you the state of stress at any angle. So those concepts will still stay because they do not, they talk of stress alone. Where will the change come? When you relate stress to the strain or to the rate of strain. That is where fluids will come. One more difference, so concepts like Mohr circle, where stress tensor change will come when stress and strain relations are used. So, Cauchy's equation which we did is still valid for fluids. Does anyone remember what is Cauchy's equation? Cauchy's equation was Newton's law applied to a point element. And what was Cauchy's equation? Cauchy's equation, you may have forgotten, this was rho A is equal to rho G plus divergence of sigma Ij. Okay? This is basic Newton's law. So this equation, because we do not talk of how stress is related to strain, we are just talking of the stress tensor, is still valid for fluids. Okay? So now, why do we want to study fluid mechanics? What is the objective of trying to study fluid mechanics? Well, fluid mechanics, fluids are something which are very, very common. Which are the two most common fluids? Water. What do you breathe? What do you breathe in? Air. What is air? A fluid. As we said, liquids and gases are fluids. So if you have forgotten, this thing should come at the top. Liquids and gases are generally termed as fluids. Okay. So if I ask, why study fluid mechanics? Then two of the most common materials in nature are fluids, air and water. Well, the human body consists of too many things, but which is one of the most prevalent constituent in our human body, which is there in each part of the human body? Blood. In each part of the human body we have blood. What is blood? A solid or a fluid? Fluid. So, not only air and water, blood is also fluid. So, if we want to now study any disease, a lot of it will be depending on what is happening to the flow of blood in different things. Hemorrhage is what? When an artery or a vein leaks. So why does it leak? Maybe, and that is when you talk of the leakage of the artery, the combination of solid and fluid comes. The artery wall is a solid and the fluid flows there. Now the wall may get weak, that has to be studied as solid, but when it ruptures and fluid starts to flow out, that is fluid. And that is where the combination of solid and fluid mechanics is needed to study all this. And so, in fact, what is being done in one of the most complex models is the whole human body. You make a computational model of this, which will consist of solids as well as fluids. And then you try to study, you take image of a person, and then you try to feed in that model. And then maybe overall try to see what is right, what is wrong. Some of the markers are there, and in fact, a lot of medicine is now moving towards this computational aspects, creating a digital twin of a human being, of a particular subject. In fact, there is research which we are doing with doctors in AIIMS on a particular disease called moya disease, which causes a stroke in the brain. So there we are trying to study what happens when blood flows in the artery And then from the MRI of the brain, can you figure out will a patient be susceptible to that moya disease or not? That means you look at the artery and you look at the various pressure and other parameters in the brain and see if at any place, there again what happens is the artery becomes weak. Some part of in fact it doesn't stay as an artery, it goes to the capillary level. It becomes weak and there is some leakage. And if there is some leakage, then that causes a stroke. So we are trying to see by looking at a patient's MRI, there are some symptoms which come before. Can you predict whether a moya disease will come or not? And if you can predict that, can you give some medications? And that is the job of the doctors to see whether it can be prevented or not without surgery. Or even if there is a surgery, then if you have that image, how do you tackle that surgery? So a lot of, well, of course that is very advanced stuff, we'll not be able to cover that, but it is needed, we need this to, and for all that, we do need how the fluid is moving. So we need the equations of fluid motion. And what we will cover in this course will be just the basic governing equations of a very simple fluid. In fact, I talked of blood. I will talk of fluid which are called Newtonian fluid. Blood is actually not a Newtonian fluid. So we will have to make some changes in the governing equations to get the equation of flow of blood. So all such stuff is there. Then, so to study, so fluid is in human body, air, blood, more fluids, bile, etc. There are a lot of fluids, so we need that. Then, so this is one aspect. Well, of course, one of the earliest reason why fluid mechanics became so popular was to study flight. What makes an aeroplane fly? If the fluid forces, and for an airplane to fly, the fluid forces have to be such that they are able to keep the aeroplane up in the air without it coming down. So some sort of a lift force has to act on the plane when it is moving so that it doesn't come down because of its weight. So forces on an aeroplane. And these forces are due to the air which is surrounding the plane. Of course, the plane has to move in a particular way. And then you will see that these forces, so you try to calculate. Basically, you look at the pressure. There is a pressure acting on the upside of the plane, a pressure acting on the downside of the plane. And the pressure on the bottom part has to be higher than the total integrated pressure on the top part for the plane to be lifted up. Okay, so flight was one of the reasons why fluid mechanics, we started studying details of fluid mechanics much more. The human body came later. Today, a lot of research is on human body. Flight also continues to be one part of research, but so another thing where you need fluid mechanics is to study the weather. That any changes, whether you will have strong winds, light winds, can you predict what the weather will be like? So again, the equations which govern the weather, whether it is clouds, whether it is rain, whether it is flow of air, are all the equations of fluid mechanics. So to study weather, in fact, what we'll find out, I'm just trying to introduce things today. I have got some time because the next tutorial will be on Monday. So I will cover things for that tutorial till next Monday lecture. But just to make things more interesting, the equations which govern fluid mechanics you'll find are non-linear. In non-linear, in solid mechanics, when we studied superposition, we could superpose things. A deformation, for example, in one of the exam problems, I don't know if you realized or not, there was torsion as well as bending. That I think it was problem 6th or 7th, where there was a rod like this and the perpendicular rod on which a force was acting. You are asked to find the deflection at this end. So there, of course, one bending will come because of the force here, but this bending is also causing a torsion in the rod which is perpendicular to that. So there, that was the only trick question, I think, in this exam. Everything else was straight from what we have done. If you just, all other 7 problems, I don't think, only other slightly tricky thing was in the shear force diagram problem, there was a force acting not on the beam, slightly away. So when you bring it on the beam, it will be a force and a moment. So that was the second, but I think we had similar things in the homework. So those were the only 2 trick parts in the exam. Otherwise the exam was straight from the homework type of problems. Let's see how you have done. I will repeat something more about the exam a bit later. So what I was talking about the weather was the equations are non-linear. And in a non-linear equation, we can't superpose. A small effect can lead to a lot of large changes. And this, for those who are interested more, this is called, in mathematical parlance, this is called chaos. Has anyone heard of the term chaos? Not like chaos in the class. Abhi main कहूँगा छुट्टी हो गई, there will be a total chaos. So I'm not talking of that chaos, but has anyone seen or heard about chaos? Chaos is a sort of a mathematical theory. There's a, where you study non-linear ordinary differential equations. And what you show is that even when you start 2 solutions which are very close, 2 initial conditions which are very close, then if the solution, if the equations are linear, what you expect is the solutions will follow almost a very similar trajectory. But when the equations become non-linear, then the trajectories can become very different. And the reason I am talking of this, and you may hear this term sometime later, so if somebody talks of this, is that in weather, if Lorentz was a person who sort of beat the equations and brought them to a very simple level, they were still nonlinear equations. And so he introduced what is called the butterfly effect. Has anyone heard of the butterfly effect? And what that meant was that if a butterfly flapped its wing in New York, it could lead to some weather effect in Beijing. So this was called the butterfly effect, which means that equations are highly nonlinear, so there can be changes which are very difficult to predict. A small change can lead to a large change somewhere very far away, which we would not expect in these linear type of equations which we have done. So again, this is what we will, when you study fluid mechanics, you see all this. Devices like which generate power, turbines, pumps, all of these work on the principles of fluid mechanics. So if you want to, all these things we will be studying now. The objective of study in fluid mechanics will be, we try to find how fluid we try to find how fluid interacts with solids which are either fully submerged in the fluid or which have a boundary which touches one or more fluids. But before that, one more example where fluid mechanics is very important are all the naval and ship applications. To be able to find out how, or to be able to control the movement of a ship or a boat or any of the device like this, once again, fluid becomes important. So now, by now you must be convinced that without studying fluid mechanics, life is, you cannot do anything in life. Everything depends on fluids only. Okay. So here what we are trying to say is, whenever there is a solid, so now how it interacts. Now, when I say how fluid interacts, then in terms of our mechanics quantities, these interactions are measured in terms of overall forces and moments. And these are examples of that. Aeroplane lifting, it's a force, but then it cannot roll around. So then you have to find the moment. So these interactions would mainly come in form of forces and moments which are applied by the fluid on the body it interacts with. As an example, let a cylinder move with a velocity minus ui in a still fluid. Okay. Now, let's talk of a two-dimensional case. So, let fx I plus fyj be the force on the cylinder due to fluid. Okay. So this is what you will try to measure. Given, let's say, there's a cylinder, it could be, I can make it an aeroplane. So then that becomes an aeroplane. So now, first if we have to make it simple, I keep u as constant. If I have to make it more complex, I will make u as a function of t. And then I want to find what are these forces which are acting on the body. Just to make the example simple, I kept it as a cylinder. But it could be any shape. Okay. So that is what, if from the fluid mechanics study, this is what we will be wanting to find out. How much forces are being exerted on this body. Okay. So, now, one thing we often do, and this we will do a lot in fluid mechanics, is if I change the reference frame, this reference frame which I am talking of, where the cylinder is moving with you, is connected to the ground. Now, if we change the reference frame and fix it on the cylinder. Now in this reference frame, the velocity of the cylinder will be 0. What is the velocity of the fluid at infinity in this case? At infinity earlier, the velocity was 0, because whatever the motion was caused would be felt around the body. So in this reference frame, this velocity will be ui, and actually far away also, on the other side also, the velocity is ui, and the velocity now becomes 0 on the surface of the cylinder, and all we have to do is subtract the two cases, since the velocity u was constant. So the effect, the equations will not change. If u was not constant, then it would have become a non-inertial frame. But because u is constant, both the frames are inertial frames. Assuming the first frame was inertial, then this is also an inertial frame, and we can apply the same equation, only we'll have to subtract u, which we have already done. From 0, when I subtract minus u, I get plus ui. So this will be done, and if you realize, I want to study flow past a car, then one way of doing that is I move with the car, the first case A, and then I measure all the forces on the moving car. Now, what will happen to the forces? Okay, before I move to that, because of this change of frame, will the forces change or will they not change? The forces will not change. Forces are independent of the frame. And in fact, even if whether it was inertial, non-inertial, the forces will still stay Fx and Fy. Forces don't change. They are frame independent. So let's write this also. So I was talking of this car example. I want to find the force the air is exerting on the car. One way of doing that is I take the car, move it with a speed in still air and measure forces at different points, integrate them. The other way of doing that is I take the still car and then have at far away air coming at speed u, which is flowing past the car, and then on the still car I put my probes, measure the forces at different points, integrate them and find the forces. Which is easier, case 1 or case 2? The second case will be easier, at least I don't have to move with the car. Of course, with advanced sensors and advanced technology, maybe I can still do the first one. And this case 2 which we talked of, so that is why this change of frame is important, because often in fluid mechanics, we study forces on a fixed body with flow around it. And this is equivalent to the moving body in a still fluid. And so what we often do is we make a tunnel in which we place the body and we have air flowing past this tunnel. We measure the forces on the body and this is equivalent to the body moving with the speed. Can you guess what is the name of this tunnel? What generic name will we call this with? This is something all of you know. Wind tunnel. Of course, in IIT Delhi, wind tunnel means something else. It's a place where you go and sit and have coffee. You don't do that? Or maybe it's people indulge in other more interesting activities in the wind tunnel. No, wind tunnel is probably a wrong place. It's too open. So there is this. So actually, wind tunnel is a very important part of fluid mechanics, where you make chambers like this and you have flow going through this. So you create flow. How do you create a flow? You'll have a fan which is either at the back of the wind tunnel, which will cause the air to come in, and then you can have different type of complex wind tunnels. There will be a rectangular wind tunnel, a square wind tunnel, a circular wind tunnel. And if you want to see wind tunnels, other than of course where you, and actually you see the wind tunnel effect even when you are in the institute wind tea, what you call it. You feel more air there or no? When you sit there, outside you don't feel the breeze, but if you are inside the wind tunnel next to the confined space, you feel breeze. And of course that you'll be able to see simply by what we call the continuity equation, V1A1 is equal to V2A2. So even if there is very little wind outside, but the area is huge, when it comes through this inside wind, V1A1, we'll derive these equations. So wind tunnel is an important part, because what we find is the equations of fluid mechanics, we will not be able to solve them for the complex cases, even computationally. So therefore, a lot of studies were done experimentally. And the experimental studies, one of the ways of doing that was the wind tunnel. And if you want to see the wind tunnels, I don't think we'll be doing any experimental courses, but we have wind tunnels in block 4, ground floor, and on the first floor. There are two tunnels with size 1.6 meters into 1.6 meters. Our wind tunnels are at low speeds. In IIT Kanpur, there is a huge national wind tunnel facilities where flows go at a very high speed, more than the speed of sound. And when that wind tunnel runs, the whole structure shakes. You can hear the sound for a long distance away. A lot of sound absorbers have been put so as not to disturb the other people when that wind tunnel runs. So these are some of the things which are there. Now, I am introducing you to some of the aspects of fluid mechanics. Another thing which you will find which is peculiar to fluids is a classification called laminar and turbulent flow. Typically what we find is when fluid flows at low speeds, then the flow is smooth. But when speeds are higher, the flow becomes in a smooth flow, the fluid flows as if it is flowing in layers. Layers are called lamina, and that is why the smooth flow, we call it as a laminar flow. and when speeds are higher, it becomes turbulent. Can anyone think of any example where such a thing is visible? All of you must have seen it. Filling of through a tap. When you have a tap and you open the valve only very little, what do you see? The water which drips out, it drips out with a smooth surface, very nicely. But as you open the tap more and more and the speed becomes high, what happens to the surface of the water? It becomes very jagged. So this difference between laminar and turbulent flow, we can easily feel when we have water flowing from a tap. So when tap opened very little, again very wrong English. Maybe Chat GPT can tell me something better. When water tap is opened very little, we see a laminar flow. And when tap opened fully, now this is not so wrong English, then what you find is that the stream looks like this, and this is turbulent flow. Okay. So now when we look at this, to us it looks like it's the velocity which makes the flow laminar or turbulent. When the speeds are low, the flow is laminar. When the speeds are high, the flow is turbulent. But actually, there was this fluid mechanics person called Reynolds. One thing I would like to tell you, something which makes me very angry, when people write Reynolds with an apostrophe S. Because his name was Reynolds. His name was not Reynolds. So, please, never in this course write this as Reynolds. It should always be Reynolds. Okay? And Reynolds came up with the criteria, and we call this as Reynolds number, and this is U times L upon nu, or rho UL upon mu. This is this is just a broad definition of Reynolds number, which you know. Rho is the density, mu is the coefficient of viscosity, and nu is equal to mu upon rho, which you can make out from these. So it is this Reynolds number, not just the velocity. So you can make the flow turbulent not just by increasing the velocity. L is a typical length scale in the flow. Typical depending on the type of flow. Suppose it's flow in a pipe, then L will be the diameter of the pipe. If it is flow over a plate, then L will be the length of the plate. So some typical length in the flow, and U is a. Now once again, in the flow in a pipe, the velocity will not be the same everywhere. So you may take it as the center line velocity, or you may take it as the average velocity. And what you find is that so this UL upon nu, or rho UL upon mu, this is what we call as Reynolds number, and high Reynolds number implies that the flow becomes turbulent. When the Reynolds number is low, then the flow is laminar. Now, high Reynolds number means, if I look at in terms of viscosity, mu will be low. Low Reynolds number means mu is high. That means when viscous effects are more, then the flow is laminar. And when viscous effects become less, then the flow becomes turbulent. So this is again, we are just introducing laminar and turbulent because we will not be turbulent flows are the most difficult to find out. G.I. Taylor, he was a big fluid mechanics person. He said, when I die and if I meet God, I will ask God to tell me how to solve turbulence. So this is how difficult turbulence is. Okay, but you should be knowing what is. It's not just I'm doing this to introduce this. No, but so it looks to us that turbulence is very bad because it causes things to become three-dimensional. So I don't know if you are in a flight when you go, and when suddenly it becomes bad, they announce that it is becoming turbulent. So please tie your seat belts. That means the plane starts shaking and all. So flow, instead of becoming smooth, becomes irregular. So in fact, when they say turbulence, we are passing through some turbulent conditions. We mean these. Then it is the same fluid mechanics turbulent we are talking of. Of course, sometimes turbulent is used in political sense also. Situation in Manipur is turbulent. You may see that in the newspaper. But in a probably corresponding way, it means the same thing. The situation at Kund was turbulent. So many people. So velocity, if you think of that as large, it has got an orderly flow. If there were 100 pilgrims going to Kund, it would have been laminar. It would have been okay. But when crores of people go, it becomes turbulent. Okay, so turbulence is also used in that sense. Okay. Now in fluid, so this is just to tell you something that turbulence is there and which we have to do. Now in fluid mechanics we have, or in general, there are two approaches to study mechanics, and the first one which we know is the material approach or the particle approach, where we follow a particular material particles and find rate of change of property associated with the particle. And we have been doing this. What is rate of change of the position vector of a particle? What is it called? Velocity. It's so simple. What is the rate of change of velocity associated with a particle? acceleration. And this acceleration is what we have talked of, what comes in Cauchy's equation, what comes in Newton's law, what comes in Euler's axiom. So let's say, now I'm going to make things, it may look like I'm making things complex. Let xp of t is the position of the particle. I put p to tell you which particle it is. When we were studying rigid body mechanics, when we talked of single particle, this was basically PJE. You did earlier mechanics, you talked of a particle. In APL 100, we talked of a system of particles which we called a rigid body. And most of the APL 100 was based on mechanics of that rigid body. Okay, so now the particle's location I say as capital XP of t, I mark it as a vector. Then what I know is dxp by dt is equal to Vp, and this is equal to xp at t plus delta t minus xp at t divided by delta t, the limit delta t goes to 0. And dVp by dt, the rate of change with respect to time, this was called as acceleration, and this was equal to Vp at t plus delta t minus Vp divided by delta t, limit delta t going to 0. And this approach, which is sort of so far, this seems to be the normal way of doing mechanics. Any law which we have is related to the particle. What is the rate of change of mass of a particle? Assuming there are no relativistic effects. 0. The rate of change of velocity is equal to acceleration. These are all kinematics. There is no Newton's law involved in all these definitions. Now this particle approach is also called the Lagrangian approach. And here we have used the superscript plus to show Lagrangian or particle approach. Now, see, you realize when we talk of mechanics or a rigid body, we talk of a ball which we throw, then there is only one particle. Now, when we talk of a fluid, then in fluid there are infinite number of particles, and we are able to study rigid body as a system of particles because they are all governed. When we combine all these particles, at least there is some law which governs their acceleration together and their angular acceleration together by Euler's first and second axioms in a rigid body. But in the fluid mechanics, if the fluid is no longer a rigid body, so particles can move on their own. So if we want to study a Lagrangian approach, we have to label the particle. So while studying fluids with a Lagrangian approach, we have to label the particle. And how do we label? A particle which is at a location x0 at t0, we call it as x plus of t0. And when we try to trace it later, then we will say it is x plus at time t comma t0. So when I say x plus of t comma t0, this will denote position of particle x0 at time t, that is particle which was at x0 at time t0. So I have to label the particle, a particular particle which is at t0 is at x plus 0. At a later time t, I follow it, and when I talk of rate of change with respect to time, I will take a d by dt of this. So this is what we call as the Lagrangian approach. But the second approach which we have is called the Eulerian or field approach, where beta we specify, we have a area domain of interest where the fluid is flowing. I specify beta as a function of x comma t, where x bar, x vector is equal to the spatial coordinate x, y, z, and beta is any property. It could be scalar, it could be vector, it could be tensor, and the particle which is at x bar at time t has the property beta. The particle which occupies this location at this time has the property beta. So when I specify things like this, this becomes what I call as a field approach, and the name given to this is Eulerian, based on the Euler, who was the first person who probably talked of this approach. And the two approaches are related. For example, if I look at velocity of v, at this red line, velocity of a particular particle at time t. When I say particular particle, it as x0 plus. The second part x0 plus is labeling. The first component t is the time. is equal to the, what is the x location? X location of this particle, which is x plus at t comma x0 plus and time t. So this is how the Eulerian and Lagrangian variables are related to each other. Okay. Now, one of the things which happens is that all our laws which we have are written for Lagrangian frame. Whereas in fluid mechanics, we will be taking the field approach. So we will have to relate the Lagrangian to the Eulerian. For example, in Cauchy's equation, the left hand side is rho a. Here the acceleration denotes acceleration of a particle. Now, if I have my velocity as a field, then I will have to write the acceleration of a particle, which is dv by dt of a particle, in terms of the rate of change of v of the field, which means the total derivative of the velocity field as a function of time, and we will see how to do that as we move in the course. So in fluid mechanics, we will be following कितने लोग हैं?
90 students and 1 0.
3 proxies today. ये लास्ट वाला है ना? ठीक है, मैं ये सब भूल जाता हूँ. आई डोंट वांट एनी. हर्षदीप, देव अग्रवाल, रक्षिता, दर्शन, वाय रविचरण, ये दोबारा मत उठाना बात. अंजलि, पी निहाल अल्केश, अरे तनिष, तनिष पूरा नाम क्या है? हाँ खुराना, ठीक है. आदित्य गर्ग, पार्थ अग्रवाल, पार्थ गुप्ता. पार्थ गुप्ता है, बड़ा सही, बहुत ही अच्छा साइन. पिछला साइन भी सेम था. एक काम करना, इन सबके जो नहीं मिल रहा है एग्जाम के साइन से मिलाना. एग्जाम में तो खुद ही साइन किया होगा ना इन्होंने. तो पार्थ गुप्ता, ये पेन या तो है या यू नोट इट डाउन. ओके, दिस वेस्ट टाइम, आई डोंट वांट टू डू दिस. विराज नरोलिया, इसका साइन ही अजीब सा. भूला प्रिशा, ओके, आई डोंट डिसाइड. अर्जुन शम्मी, शम्मी. संस्कृति, संस्कृति पूरा नाम बंसल. ओके. साहिल, ये पक्का गलत होगा. अर्णव गर्ग, देखो थोड़ी तो हमें भी अकल आ जाती है. आई नो यू पीपल आर मच स्मार्टर. तुम्हारी स्मार्टनेस तो मैं कभी इक्वेट कर ही नहीं सकता, बट स्टिल. देन लेट्स सी. अमन कुमार, कुमोदनी, आयुष, शाहरुख खान. नहीं, कोई नहीं था, मैं ऐसे ही बोल रहा था. अभिनव कुमार, सुगंध आनंद, दीपांशु, आशुतोष राज, केशव मेहता, केशव मेहता नहीं है। तो ऐसा तो नहीं आके चला गया, किसी ने देखा था उसको? नहीं देखा, ठीक है। वो बेनिफिट ऑफ डाउट दे रहा था, पर नहीं, कोई देना नहीं चाहता उसको, कोई दोस्त नहीं है। खुशी ऋषित श्रीवास्तव, अजय के, सिद्धार्थ सिंह। तुमने पहले तो नहीं उठाया था हाथ? नहीं, अच्छा पूछ रहा हूं। हार्दिक, हाँ एक और, हार्दिक बुजारिया। यानी कौन साइन कर रहा है अभी? प्लीज डोंट डू द 15 एक्स्ट्रा सिग्नेचर्स। आई एम श्योर एक बंदे ने तो किए नहीं है। देयर एटलीस्ट 10 पीपल। अज्यूम 5 लोगों ने डबल किया, बट व्हाई डू यू डू ऑल दिस? इन लोगों की अटेंडेंस फिर काटनी पड़ेगी सबकी, और नेक्स्ट टाइम ऐसा होगा तो अपन सबकी अटेंडेंस, जितने बैठे हैं ना, उन लोगों की अटेंडेंस में से काट लेंगे। हाँ, रैंडम 15 नेक्स्ट टाइम। व्हाट आई एम गोइंग टू डू इज, टुडे आई एम वेस्टिंग माय क्लास टाइम, आई डोंट वांट टू डू दिस। नेक्स्ट टाइम दिस हैपेंस, प्लीज लिसन, और अपने दोस्तों को भी रिकॉर्ड करना सुना देना जो नहीं आए हैं। नेक्स्ट टाइम दिस हैपेंस, जितने एक्स्ट्रा लोग हैं, आई विल रैंडमली कट दैट मेनी पीपल्स अटेंडेंस। अब क्या करें, करना पड़ेगा। तो हो सकता है कुछ तो उन्हीं की कब जाएगी जो नहीं आए, पर कुछ जिन लोगों ने साइन किए हैं, सब ऑफ यू हैव साइंड इट, सो प्लीज डोंट डू दिस। पूरी क्लास की काट दो, सबका, सबका इतना पागल नहीं है, सबके बराबर, वो सबका ही बराबर हो जाएगा, कोई फर्क ही नहीं पड़ेगा, कोई फर्क नहीं पड़ेगा। मूसा बिन, ओके, जाहनवी, जाहनवी नहीं, हाँ ये जितने 2 क्रॉसेज वाले हैं ना, वो सब मिल गए। बड़ा क्लियर कोरिलेशन है, जिनके पहले के क्रॉस है उनकी अधिकतर लोगों की प्रॉक्सी है। आदित्य तेजवाल, देखो एक और केस। आई थिंक दिस इज द वे यू कैन इजीली अनमोल। अच्छा चलो, यू गो, एक्सेप्शंस प्रूव द रूल। सुबोध बंसल, अच्छा एक्सेप्ट, अनदर एक्सेप्शन। ऋषभ कुमार, यार तुमने तो पक्का उठाया था पहले हाथ, नहीं। अवीन गौर, नीलम, कृषा, कृषा करवा, कृषा करवा भी लिखो भाई। पार्थ शर्मा, वहां से ध्यान रखो, कई लोग दोबारा हाथ उठा रहे हैं। सिद्ध बंसल, जागृति, ये पक्का नहीं निकलेगा। यश, हर्ष बगोटिया, हर्ष बगोटिया लिखो भैया। इन सबके एटलीस्ट 3-3 काटेंगे हम अटेंडेंस आज। रोहित कुमावत, अब वो कहेगा मैंने तो कहा ही नहीं था, किसी ने मेरे बेआब पे साइन कर दिया। आई वुड, ये भी देखना नहीं निकलेंगे। गजल शर्मा, सॉरी, आई नॉट प्रिडिक्ट एनीथिंग नाउ, सारे मेरे प्रिडिक्शंस गलत हो रहे हैं। अनिल सैनी, आर्यन, आर्यन पूरा गुप्ता, हाँ ठीक है। विपिन पूरा बंसल, ठीक है, ये तो हो गया। फटाफट फटाफट लेट्स सी, इसमें तो कमी है। पी श्रीधर नायक, ये गलत लग रहा है। तेजस्वा सिंह, अरे वाह, आई एम बैड एट प्रेडिक्शंस। वो एआई का मेरा मॉडल ठीक नहीं है, अच्छा न्यूरल नेटवर्क लगाना पड़ेगा। अपूर्व पूरा, आयुष कुमार, ऋषिका गर्ग, करण शर्मा, सार्थक सोमेश्वर। मेरा साइन ऐसा है विच रियली लगता है कि किसी और के लिए तुमने बनाया है ये साइन। दिशा, दिशा, सॉरी, अभी तुम्हारा एब्सेंट मार्क हो जाती 3। अनुज मंडल, इसकी तो साइन ही अलग है यार, साइन ही इसने गलत किया है। मिताशी जैन, अर्नब गर्ग, अर्नब गर्ग भाई इसकी भी लिखो। मंजीत सिंह, ओके। आकाश, ध्रुव चौरसिया, ओके। माही, वाह, ओके। माही के नाम से मुझे धोनी याद आता है, तो दैट इज व्हाई आई सेड वाह। सात्विक, सात्विक है, सात्विक गर्ग नहीं है ना, नहीं। आर्यन चौधरी, एक और, चलो इसका भी नहीं मिलेगा, देखना। केशव मेहता, केशव मेहता नहीं है ना, नहीं। पी शशांक, ओके। सार्थक गर्ग, ओके। चहक शाह, चहक शाह नहीं है। के साई किरण, ओके है भैया। आर्यन पचौरी, ओके, हाँ प्रेजेंट बोल दो। दीपांशु शर्मा, आदित्य निशांक, ओके। रुद्रेश, कितने और आएंगे यार, ये तो बहुत ही चक्कर है। भव्य बहुगुणा, निखिल मिश्रा, मोहम्मद अदान, पहले नहीं उठाया था ना, ठीक है। आदित्य तेगवाल, अच्छा कुछ नाम मेरे को लग रहा है दोनों में साइंड है, तो दोनों में मत साइन क्या करो भाई। ये आदित्य तेगवाल आई थिंक इट साइंड अर्लियर ऑल्सो, तुम्हें 2 अटेंडेंस नहीं मिलेगी 2 बार साइन करके उसी दिन, जो भी है। विवेक कुमार, विवेक कुमार नहीं है, नहीं है। पिंशु, पिंशु भी नहीं है। प्रांजल गुप्ता, प्रांजल गुप्ता लगातार 3, वाह, ये भी नहीं है। सुधीर यादव, हर्षराज, हर्षराज सिंह, इसके भी गलत साइन लग रहा है, साइन भी ढंग से नहीं कॉपी कर सकते हैं लोग। कुणाल मेहरा, हिमांशु, पूरा नाम, फुल नेम हिमांशु वाडीवा, ओके। सप्तऋषि बनर्जी, ओके। अथर्व सराफ, अनुराग, ओके। के जयदीप महेश, प्रेजेंट, ओके। वर्षा यादव, एन पी राठौड़, राहुल, ओम राठी, गौरव व्यास, पी रेड्डी, PSM रेड्डी, isn't it? ऋतिक रावत, इशिता जैन, आर राशि, ऋषिका राशि, अच्छा तो आपने पहले एकदम बोल दिया करो ना। सौरभ मीना, हार्दिक सिंह, उज्जवल जैन, ओके। अब लास्ट पेज बस। आर्यन देवनारायण, कौस्तुभ, दृशा विपुल, ये तो नहीं होगा, नहीं ये हो, निशील भी है, ठीक है। संस्कृति अग्रवाल, ओके ठीक है। बट प्लीज वी आर वेस्टिंग, आज वालों की 3 अटेंडेंस जाएंगी जिनकी भी एक्स्ट्रा लगी है। प्लीज जो दोस्त लोग थे, सोचो तुमने अपने, अब क्लास तो मैं क्या पढ़ाऊंगा आपके बाद, तुमने अपने दोस्तों का कितना बुरा किया है ये सोच लो, कि उनकी जो 3 जो फ्री अटेंडेंस मिलने वाली थी आई वाज गोइंग टू काउंट 25 आउट ऑफ 28, वो तीनों तुमने छीन ली। तो उनकी गलती नहीं है, गलती तुम लोगों की है जिन्होंने साइन किया है। कल्प्रिट्स आर यू, नॉट दोज पीपल। उनका नुकसान पहुंचाने वाले तुम लोग हो।